last course on singular foliations by Camille Laurent-GENGOUX from Institut Élie Cartan-Gengoux. And so I remind you, as other chairs have already said, this is supposed to be a lively course, so please don't hesitate and ask questions. All right. Thank you.
Thank you. So Eva, where is she? Sorry, she's not here. Okay. And as I said, Cedric, I really would like to thank you for giving me an opportunity to explain to young Poisson geometers that actually, oops. Okay. That actually, this is certainly already met singular foliations. Just you weren't told they are singular foliations, probably. But you didn't notice, it appeared as just a bunch of uninteresting leaves, some green, some brown, doesn't look fascinating. You met at least two of them. One in Henrique's class yesterday, he explained you that symplectic foliation of a Poisson structure is a singular foliation. But also in Anna's class, we had orbits of group actions. That's also a kind of singular foliation. And I'm going to try to explain why probably it goes unnoticed. It's because it flies under the because it's too basic as an object. So what I'm going to do first is to tell you what the definition is. Because when you know the definition, maybe you notice it. And it's not an easy point. I strongly invite you to read an article by Sylvain Lelavaux, to take a historical mathematical notes on the debate that was in the 70s with Hermann, Stepan, Sussman, and Nagoya, and some others, about what the correct definition of a singular foliation should be. It's a debate that took place in the 70s. I'm going to kind of, in an anachronistic manner, to kind of open that debate again and try to close it by trying to give what I would call the consensus definition of what a singular foliation is. I don't like the word consensus because we are, as scientists, we'd like to reject consensuses, but still I will use it. And I will explain you what kind of structures do singular foliation hide, because I see this interesting bunch of leaves. Okay, this doesn't work. Yes. Anyway, when you look more closely at the center of the picture, you see a snake, in fact. See? So, and after you see the snake, it takes a little time to think that, oh, that's actually a snake. But after you saw it, there is no way you can unsee it. And I think the peculiarity of singular foliation is a bit like that. The hidden structure that are behind, if nobody says, during a long time, nobody told me that they existed, so I didn't pay attention. And at some point, I saw that there was some venomous snake hidden in them, and I started to pay attention. And now there is no way, when I see a singular foliation, that I don't see the snake. And I hope to show you like that. One of the reasons, I think, that made singular foliation something that was around, wasn't forgotten, but that's very not studied much by itself. That's a little bit like cheese. You don't know if you like cheese or not, because there are too many kinds of cheese. And something for singular foliation, you have too many kinds of singular foliations, and in particular, as I will explain, too many different definitions of what a singular foliation should be. And because of this manifold of definition of examples, I think people got a bit uninterested. Another reason, I think, that made singular foliation flew under the radar, it's a bit like wine and cheese. although we discovered yesterday that there are some very good ones here in Catalonia, it has been since the 1965, it has been a very French as a subject. So after the Stéphane Sussman debate on definition, like 20 years was the subject were a bit forgotten. The only articles I know on the subject are by Dominique Servault, Pierre de Dazor. I'm going to say a few words about this. They're even written in French, actually. And then there was a singular foliation renewal due to non-commutative geometry, with, in particular, Georges Skandales, Iakovos Androulidakis, well, he's not in France, but yeah, Claire Debord, and some other mathematicians in non-commutative geometry, like Omar Moshen, Robert Yayunkan. And I would say, nowadays, on singular foliation, that's certainly the most active school. In particular, this school arrived with an object I will describe tomorrow, which was a holonomy groupoid of a singular foliation, and I will speak about that. But I will not enter too much into what they did. They more or less developed the analysis of singular foliation. I'm going to speak more on the geometry of singular foliation. There were other groups, other mathematicians like Thomas Strobel that studied singular foliation for reasons coming from theoretical physics in Lyon. And now there are people in Toulouse around Bertrand Toen, Gabriel Vezozzi, who study singular foliation from the point of view of derived geometry. I will not speak about that. I'm not competent in derived geometry, but it's also something that exists. So you see, all these groups are in France. There are also singular foliations in holomorphic complex geometry. So I hope that I will make it more international by giving you definitions and the hidden snakes behind singular foliations. So, first question, first problem. What is a singular foliation? Towards the definition, section 1. Just one thing. When I say a submanifold, by default, it's immersed submanifold. So it may circle around itself. Okay. Well, foliation, it's supposed to be like a lasagna dish, like you have your manifold and it's cut into submanifolds, all of the same dimension. Or a spaghetti dish, same thing but with leaves of dimension 1. So you would expect singular foliation is the same thing, but some leaves are maybe points, some leaves are curves, some leaves are other surfaces, or even open a subset. Well, you would expect just, it's the same thing, but the dimension of leaves change. So here is the most basic definition, what can come out of what a singular foliation should be. You take a manifold M, and you assume it is a disjoint union of immersed submanifolds, not all of the same dimension. Said differently, you have a map from M to submanifolds. I'm just thinking the notation, but I write like this to a point M. It maps its leaf through M. That's a very basic and elementary way to define singular foliation. But I didn't use that word. It's just partition by submanifolds, because I want to insist that partition by submanifolds are important, but are not a good notion. We made up a very sloppy name that we decided to call them partitionifolds. And the sloppy name is chosen on purpose, because since you have a name, I hope you will remember it better. But since it is a sloppy name, I hope you will understand that's not a good definition. That's a dead end. But it's around. I mean, singular foliation properly defined should induce that, right? But it's not. Okay. So why is this not a good definition? Well, all kind of counter examples. Like, okay, the pinch. I take the horizontal line. Then I take a curve that does something like this. It goes like this. like this. And here it has one at a tangent, which is a vertical. Like take the graph of this function, for instance. You see the derivative at 0 is infinite. And you take also a multiple of this, like that, assume you had a spaghetti and you pinched them. I'm saying that's not a good example. Even worse, take a magnetic partition manifold. It means you have a circle with electric current in it, and you look at curves of the magnetic vector field. So what do you have? You have a circle like this, around which you have many circles, and in the middle you have a straight line. I'm saying these are decent partition manifolds. Somehow they are regular. All the leaves have the same dimension. But there is no way you can do geometry with this kind of things. They are really way too bad. I'm sorry if you want to sleep tonight, but I can, if a theorem, you can make R3 the disjoint union of the circles, all of radius different from the 0. Yeah, sorry that I spoiled your night, but you will think about this problem. But it's just the circles are in a very nasty way, but there is a way. Okay. We don't want, obviously we don't want that, because there is almost no property that this kind of things is satisfied. Sorry? No, the problem is that here you see the current thing, the tangent space is like this, while around it goes like this. No, it's not half of a vibration. So why? Well, I say almost nothing can be proven. There is still something that can be proven. Lemma. Let R be a partition manifold. And I consider FL the vector fields which are tangent to all leaves. Sorry. So vector fields on M, let us assume compactly supported, such that Xm is in Tm Lm for all M in M. So you see, I take vector fields that are tangent to all leaves. Like, for instance, such a vector field here has to be 0 at every point here. Here it has to be 0 here, because the tangent space there is vertical, except here it is horizontal. Okay. Well, take some X in this guy. It's compactly supported, so the flow exists. Its flow at time t, it's a map from M to M. It's a diffeomorphism. And theorem, it's an isomorphism of partition manifolds. In fact, it maps each leaf diffeomorphically into itself. Okay, is an iso of partition manifolds. It's not easy because it's not because a vector field is tangent to a sub-manifold that it flows preserve it. Just assume that's a sub-manifold in R3, and you take a vector field which is like this. It is a tangent at all points. So that's a square. Forget the boundary. It's tangent at all points, but the flow doesn't preserve it, right? But here, using the fact that L is a partition, using the fact that it's locally true, and using the fact that 0, 1 is connected, you can prove it. So at least there is one property that these partition manifolds, generic partition manifolds, do satisfy. If I take a vector field tangent to all leaves, its flow is a symmetry of the partition manifold. That's something that will come back again and again. Well, so obviously we have to impose more conditions, and there you have to make a choice. Do you want to study spaghetti dishes where you forget an isolated lasagna? Or do you want to study lasagna dishes where a few spaghettis were forgotten. And it's perfectly fine to have an isolated lasagna into a spaghetti dish. You have these kind of things if you consider, if you define foliations. If you define a foliation with forms, or you define them as fibers of algebraic map from Cn to Cm. As far as I understand, this would be the definition of Bertrand Toen and Gabriele Vesozzi, researcher in derived geometry. So very low isolated lasagnas in the spaghetti dish. But if you want to do geometry in the spirit more of Poisson geometry, all things you can allow is isolated spaghetti, like have one spaghetti like this, and then you have lasagnas like leaves of a book around it. This is okay. And what the additional condition one has to put on partition manifolds to allow isolated spaghetti in lasagna dish, but not isolated lasagna in spaghetti dish, is smooth partition manifold. So what is a smooth partition manifold? It's a partition manifold to start with. So that if I take a point on the manifold, and if I take a tangent vector to that point, there is a vector field through that tangent of a vector, which is tangent to all leaves. Okay, like isolated lasagna, it doesn't work. This vector field, there is no way you can find a vector field through that vector. Sorry, this tangent vector, tangent to the lasagna. There is no way you can make it. You can find a vector field tangent to all spaghettis through that vector. If I come back to these examples, also it's not smooth. Like if I take something tangent to the circle here, if I take this vector here, that. So smooth partition manifold seem to be quite good. And question I will ask now is, should you just say that the singular foliation is a smooth partition manifold? I'm going to argue that yes, then no. They are perfectly fine. Smooth partition manifolds. They satisfy many things that for you, those of you who are used to Poisson's geometry, sound quite familiar. I have nothing to erase, do I? Like, if you travel along a leaf, it's always the same thing. That's something well known in Poisson geometry. If you take a symplectic leaf, you take 2 points. Well, you have a neighborhood of these 2 points, which are diffeomorphic as Poisson open balls, as balls with a Poisson structure. The same thing with smooth partition manifold. This lemma proves it, right? Because smoothness and this lemma says you can always go from one point to a leaf to another point in the same leaf by following flows of vector field tangent to all leaves, which are therefore symmetries of the partition manifold. Good. Well, that's more. And so I say every leaf, again, in Poisson geometry, that's well known. If you have a symplectic leaf, there's a transverse Poisson structure. Same thing for smooth partition manifold. I take a point, I take now a sub-manifold that, see, the leaf goes like that, and the sub-manifold goes like this, call it sigma, so I want TL sigma, direct sum TL LM to be the whole thing. I call that a transverse sub-manifold, like a transverse small disk. Well, for Poisson structure, it's known, it's called Dirac reduction. I don't think you spoke about it yet, that you have an induced Poisson structure. Same thing with smooth partition manifold. If you take a disk, well, look, at this point, the sum is the direct sum, and by smoothness, it's going to add up, maybe not the direct sum, at every point. So every leaf, that's enough that for 2 submanifolds, so that the intersection is a manifold again. So, in fact, it's written here, It's easy to show. If I take sigma transverse, this assignment is again a smooth partition manifold on the transversal. Moreover, it is unique. So if I take another disk somewhere else on the same leaf, also transverse, I also get an induced smooth partition manifold there, and guess what? At least near the intersection point, they are isomorphic. So not only the transverse smooth partition manifold exists exactly like in Poisson geometry, the transverse structure exists, but they are all isomorphic. Good. And something else, you know, in Poisson geometry, that if I have my leaf, if I have my transversal, you have the Weinstein splitting theorem that says you that, sorry, I have my symplectic leaf, I have my transverse structure. The Weinstein splitting theorem tells you that near this point, in fact, it's isomorphic just to a direct product of L times your transversal. You see? Weinstein splitting theorem, the way, maybe not presented that way yesterday, but it says exactly that. Same thing for smooth partition manifold. Near a point, the smooth partition manifold is a direct sum of the leaf, the very stupid foliation with one leaf, times the transversal. Okay, so this seems to be a very nice object. More than that, when you have a smooth partition manifold, you have a singular distribution. M maps to TMLM. Why do I call it a singular distribution? Because to each point, you associate a tangent space. You associate a subspace as a tangent space. The dimension may change, but it's like a distribution. That dimension may not be constant. And this singular distribution is quite good. So if I take the section is closed under lib bracket, I mean, two vector fields tangent to all leaves are tangent to the leaves. If I take a section of this guy, the vector field tangent to a leaf, so its flow preserves the leaf, so in particular it preserves that distribution. For those who know Stefan-Stutzmann theorem, it's that. The dimension is upper semi-continuous, exactly like the rank of the Poisson structure, very similar to Poisson structure, which means that if here you have a leaf of dimension 5, we are sure that around the dimension of the leaves around maybe 6, maybe 7, maybe 5, that cannot be lower. The dimension has to go up. And because you have that, when you have something which is valued in integer, which is upper semi-continuous, well, look at the points where it's a local maximum. It has to be, that's an open subset, which is dense always. We have a dense open as a subset where this M goes to where the dimension of all the leaves, where the dimension of the leaves, the dimension of the tangent space are constant. Sorry, this was very badly said. Let me say it again. Just because smoothness implies that the map from M to N, where in fact one dimension, one dimension of M, mapping M to dimension of TMM, of TMLM, that's upper semi-continuous, which means that there's an open dense subset where it is like a constant. Okay, it's constant, so what do you get? Of course, you get just a good old regular foliation. So, a smooth partition manifold. In particular, there is an open dense subset where it's just a regular foliation, the good old regular foliations. And on the singular points, so the points which are not of this type, the dimensions are smaller. They cannot be ever bigger. So you already have lasagnas, the regular leaves, which are dense and open. And you have the complementary of a dense open subset where you may have spaghettis, leaves are smaller with a dimension. All that is very similar to Poisson geometry. All that is very good. So, is it a good definition of a singular of a foliation?
But you could have on this certain subset where the leaves all have the same dimension.
Yeah.
Open subset of different dimensions. Leaves of different.
Yes, like this. I take just an R, I take this, and then I take points. But it's the same for Poisson structure. I mean, I could take a function, I could take an R2.
It's just a regular foliation, usually.
Right.
Foliation,
yeah. It's a union, yeah. You're right, in fact, yeah. Yeah, it's an open set on each component connected. Oh, good point. So theorem, when you have, I just made it up, sorry. But I think it's so. When you have a smooth partition manifold, you have an open set on each connected open dense set, and on each connected component, you have a regular foliation. That's the dimension of the leaves may jump from. Yeah, good point. Like in this case, the only singular point is this point. Yeah, very good. Sorry, thank you. Okay, so let us vote. Do you accept that as a definition of singular foliation? No? I failed? I failed in convincing you? Maybe you should not. Now I'm going to give what I call the consensus definition, but maybe you should reject consensus. Maybe that's a good definition. I don't know. In fact, I think in complex geometry, somehow they still use it. So here is now, I'm going just to give it the consensus definition. It's me who made up these names. Don't blame even my co-authors, maybe, of what a singular foliation is. And okay, what is it? I go slowly, alpha, beta, gamma. So you take a subspace of compactly supported vector fields. This in Poisson geometry we don't like, compactly supported, not our best one, but okay, compactly supported vector fields. A subspace, I call it F. And I want three conditions, alpha, beta, and gamma. I want involutive. I want this to be a symmetry module. I want this to be locally finitely generated. So involutive, it means what? I have a Lie bracket here. I want F bracket with F to be inside F. Okay. Symmetry module, it means symmetry module. I mean, if I take X, what have I written? Anyway. Well, anyway, if I have X in F, a function, I multiply the vector field by that function and it's still in F. Yeah, forget it. And I want locally finitely generated. So that's slightly tricky what locally finitely generated means. You can change from authors to authors, but it's all equivalent. But it's a bit tricky. But it means that for every point, I have vector fields. I have an integer R vector fields in F, and a neighborhood, such that for any X in F, there exist globally defined functions fi, so that X minus sum of the fi xi is 0 here, but maybe not 0 outside. It's a little bit tricky. I decided to kind of, okay, just accept it means that it's locally finitely generated as a module of a smooth function. Just remember that there's a little snake hidden under these leaves, and just let us continue. Okay? Okay. So, if I were you, I would complain. I mean, how can I call that a singular foliation? I just have a stupid families of vector fields, and there is even no leaves, right? This cannot be called a singular foliation. Show me the leaves. Okay. And so, first of things, what do you think the idea is behind that? What is F supposed to be of the leaves we don't have yet? Sorry? Exactly. So in fact, we define singular foliation by saying, okay, take the leaves, they don't exist yet. Look at vector fields tangent to all leaves. And well, it's involutive, it's a module. Not always finitely generated, but let us assume it. And Like in this example, it's not finitely generated, for instance. But if it's a decent foliation, if a descent is good finitely generated, let us take it as a definition. Okay? Yeah. Good question. I'm going to get rid of this assumption quite soon. I think one of the reasons that people in non-complex geometry want to do analysis and compactly supported is important. But in fact, it's not really necessary. Actually, Germandia, in his PhD, clarified that. Alfonso is here? Yeah. Yeah. Okay. So don't worry. In how much time do I have left?
28 minutes.
28 minutes. Oh, good. So in 28 minutes, I will give you a theorem saying that leaves exist. Singular foliation. In that sense, they do have leaf. Good. But it's hard. It's not an easy theorem. Okay, so I gave you something that seems very weird, and I claimed the consensus definition, and we like to reject consensuses. How do you pronounce that? Consensuses? Anyway. So now I have to argue with this definition if okay. So why compactly supported? We can get rid of that. In fact, probably better to use sheaves. So you are perfectly entitled to hate sheaves even more than compactly supported things. Then whenever I write sheaf, just erase or replace by a local. Okay, it's enough. So a singular foliation, you can see it as a sub-sheaf of the sheaf of vector field, which on each open set I have a bunch of vector fields. And same condition. Involutive, it's a sheaf over the sheaf of smooth functions. I mean, you can multiply by any function on your open set, and it's locally finitely generated. Again, there is a snake hidden there. Locally finitely generated for sheaves, it's not that easy. You don't want, when you have open subsets smaller and smaller that converge to a point, you don't want the number of generators to go to infinity. Locally finitely generated, just open a book on sheaves. Look at the definition, it says, there is an integer r, so that for any small enough open set, these r elements generate on each one of the open set, even the smaller one. Again, I don't want to open that box. You open a book on sheaves, you read the definition, and you close it. Okay. So just say there was subtlety there. Well, the good point with this definition is that maybe you prefer to work in the holomorphic world. And in the holomorphic universe, there is no global object, certainly not compactly supported objects. So you have to use sheaves. Then, yeah, I don't want you to see that yet. So then a singular foliation becomes a sub-sheaf of the sheaf of local vector fields on the holomorphic and complex manifolds. Same condition, it has to be involutive. It has to be a sub-sheaf of module over holomorphic functions, and it has to be finitely generated again. But in fact, the last assumption you can cross. Why? Because germs of holomorphic function are Noetherian. So anyway, any subsheaf is going to be locally finitely generated. Okay? Same thing with real analytic, same thing with algebraic. Like, what is a singular foliation on an affine variety? What do you think it is? Well, I take all polynomials in n variables. I want to have, well, a vector fields. It's just derivations of O, right? Derivations of polynomials are polynomial vector fields. And what do I want? Alpha, F included in F, then O, F is in F, that's invertive, that's a module. And do you think to have to say locally finitely generated? No, because polynomial functions are in a Noetherian, and any submodule is finitely generated anyway. So when you work with holomorphic, real analytic, algebraic, which is going to be done by Ruben of a Thursday, this third assumption it's there, but it's just automatically there. So you don't need to add in the definition somehow. Okay. Okay, so.
Maybe what would be natural question, if you go back to the earlier definition, why don't you just skip complex supported?
Because of the infinite comb. Next slide. The infinite comb is very annoying. It's a comb like this. The comb is, you know, to dress your hair. Part here, but next slides. Well, okay, I have to justify now this definition. So I'll give examples. There is a wide class of examples. Oh, symplectic leaf, that's so stupid. Anyway, yeah. What do you want to have a singular foliation? You want to be able to take any Lie algebroid, obviously. So, yeah. Examples. First class of examples, when you have a Lie algebroid, well, just take all sections, you take all the section of the Lie algebroid, compactly supported as a section, if you want to have compactly as a supported, you apply the anchor map, and you get vector fields that obviously satisfy all the three items required here. It's locally finitely generated because the rank of the Lie algebroid is finite. It's a symmetry of M module, it's involutive. So, image of the anchor map of a Lie algebroid, that's an example of singular of a foliation. In particular, if I take a Poisson structure, pi, I take pi dash of all one forms. I don't know if you explained pi dash, Henrique, already? Well, anyway, you take the symmetry module generated by whole Hamiltonian vector fields. That's.
Didn't say what the algebraic was.
Yeah. Okay. Right. I take it to advance. Yeah. For Lie algebra, it's the next lecture. Image as an anchor map, our example. That's perfect, in fact. But anyway, our example of singular foliation, which also means that if you have a Lie group acting on a manifold, we can take the transformation Lie algebra. It means you have a map from the Lie algebra of this Lie group to vector fields on M, like x done x bar, and then you take all f x bar, f compactly supported of a function, and this is again a singular of a foliation. So whenever I have an infinitesimal action of a Lie algebra, or have an algebroid, or have a Poisson structure, I immediately have a singular of a foliation. Good. So Poisson structure is included. Now, here is another example. I want to spend some time with this example. It's going to be, again, the exercise by Ruben next Thursday. It's vector field which are tangent to a something. So I'll be more precise. I take a function phi. That's an important example. I take some function phi on Rn. Yeah. Now I define f phi to be all vector fields on Rn, compactly supported maybe. Well, not forget compactly supported for the moment, such that x of phi is a 0. So if you want, these are infinitesimal symmetries of the function phi, functions whose flow preserve phi. Okay. Is it a singular foliation? Well, obviously, it's a symmetry of M module. Obviously, it's closed under Lie bracket. The Lie bracket is a commutator. So again, I will ask the crowd his opinion. Is it finitely generated in general? Who votes yes? Okay. Who votes no? Yeah, you're right.
Any kind of flat,
Exactly.
flat functions create all kind of counterexample.
Yeah, exactly. You take a function which is 0 here, non-zero here, and have a counterexample. More complicated. I take a polynomial function polynomial in n other variables. Is it finitely generated? Who votes no? It's a hard one. Well, you may think, of course it is. Polynomials are a Noetherian. Any module is finitely generated. So yes, it is finitely generated. Oh, but no. Because what I prove like this is that polynomial vector fields killing the function phi, it's a finitely generated module over polynomials. I haven't proven yet. It's true of smooth polynomials. So it seems not to be, but in fact it is. Because you have the theorems that say things like germs of smooth functions are flat over polynomials. No, the opposite, sorry. Anyway, there is notion of flatness in algebraic topology, which says that in that case, the smooth module of vector fields that kill this guy is in fact has generators which are polynomials. So it has finitely many generators. By the way, it's again a thing. All these theorems are in book by Tougeron, article by Malgrange. It's only written in French. I couldn't find any English version of the theorem I speak about. I'm sorry. Maybe Eva, you know one. But the only reference I know are Tougeron, Malgrange. And this flatness, is there a non-French reference about that?
Non-French?
Yeah, not written in French.
Oh my God.
Yeah, okay.
Oh dear.
Sorry? That's written in English, of course.
Borel, I mean, everything starts with Borel, right?
Yeah, anyway, it's true. So if you take phi polynomial, even if I consider smooth vector fields, that's still a finitely generated, look at generated, so it is a foliation. Other example, well, so I have to justify my weird definition. And you see, with these examples, that in fact, quite often when you want to study a problem, what is given, it's not the leaves. The leaves come after. Think of a Poisson structure. What you are given is a bivector field. You don't have the leaves a priori. It's a theorem that leaves a smooth partition manifold is going to exist. Same thing here. Like if I take all vector fields that kill this function, see? What are the leaves? It's not clear. Like assume phi equal to 0 is something a bit weird, like something like this with plenty of the torus of cones on the top of it. What are the leaves? The leaves are not given a priori. But the vector field tangent to the leaves that don't exist yet are given. So I think that's the main justification. That's why I call it the consensus definition. But when you work on that, you'll see that quite often the leaves are not given. The leaves will come as a theorem. What is given are vector fields tangent to the leaves that don't exist yet. Now, I will give another type of justification. Take a point in R2 and in Rn, and take all vector fields that vanish at this point. Okay? Take all vector fields that vanish at order 2 at this point, that vanish on the first derivative of the vanish. Again, close the curly bracket. Again, it's a module. And it is finitely generated. Like for this guy, here are the generators. You have 4 of them. It's Adamar with a theorem. Ruben is going to say more tomorrow. For this guy, we have 6 generators. And same thing with dy, dy, dy. Okay? So these are 2 examples of symmetry of R2 modules closed under the bracket, finitely generated over symmetry of R2. And well, I haven't explained what leaves are, but what do you think they are? If I take all vector fields that vanish here, what are the leaves, you think? This point and the rest. Okay, what are the leaves here? This point and the rest. You can always go from here to here. So you have 2 different singular foliations that have the same leaves. So in some sense, it means that if you only look at the leaves, you are losing information. You have more information when you consider F than when you consider smooth partition manifold. And the map from singular foliation from smooth partition manifold is not going to be injective. It's not surjective either. It's not injective. Okay, I'm not going to speak about that, but it's funny that if you take concentric spheres around the point and the point, somehow you can see this kind of singular foliation as a Lie algebroid, as a symplectic foliation, vector fields tangent to some functions. You can see it as any one of these examples. Anyway, oh yeah, by the way, also representations can be seen as singular foliations because a linear map, because a linear map can be seen as a vector field. When you have a vector space, you have a correspondence with linear maps on vector fields, which is a Lie algebra morphisms. Anyway, just to say that theory. Okay. Okay, so that's my first justification. Second justification of the definition of singular foliation is that, well, all nice construction you can think of do actually exist for singular foliations defined as in this so-called consensus definition. Yes?
Is there any reasonable equivalence relation between what you call a singular foliation to make this a bijection with the leaves?
Why do you ask this question? Yes, that. I think so. Yeah, so in fact, I even don't have. Well, it's exactly about that you have all theorem of Stepan on the Sussman.
Right.
That says that when you have a smooth partition manifold, it's more the same thing as distributions, smooth distributions of a certain type. The certain type means you have in sections of this distribution, you have a submodule where the flow preserves the distribution. It's not easy matter. So this have a one-one correspondence, smooth partition manifolds, and smooth distributions with good properties. With this F, I don't really know. I think if you work in holomorphic setting, then yes, because you take a smooth partition manifold, holomorphic one, take vector fields tangent to it, it's finitely generated, so you have no problem. And you have a one-one correspondence between, I just made up the theorem, okay? Is it recorded? Yeah. I think in the holomorphic case, I'm pretty sure this works. One-one correspondence between smooth partition manifolds and modules of a holomorphic of a function that are primes, in the sense that if fx is in the module f a function x a vector field, then so is f. No. Is it true? I'm not so sure, in fact. No, sorry. Yeah, I don't know. Good question. Okay, short answer, I don't know. Yeah. So I wanted to say that with this, what I call consensus definition, you have quite a lot of natural constructions that do work. Direct product, fine. Well, a pullback through a submersion, like you have a manifold here, you have a manifold here, and a submersion here. You can take a singular foliation here and pull it back. Basically, you have to add all vertical of the vector fields. It works. You can also have restriction to transverse submanifolds. So this I have to explain because it's very nice. You take sigma in M, you have a singular foliation here. You can consider on F as a sigma. So I do that. I restrict to sigma all vector fields on M tangent to sigma. It might not be finitely generated, but it's a module, it's closed under brackets. And if you are transverse to the foliation, it is finitely generated. So that's a singular foliation. You can do a suspension through a symmetry. So you have a singular foliation on a manifold M. You have a symmetry, so a map from M to M that maps F to F. You can do the suspension and that's a singular foliation. For instance, if you take vector fields tangent to this concentric as a circle, and if you take like multiplication by 1/2, homotopy by 1/2, it's a symmetry, and you make the suspension, we'll get the self-eating snake. So let's imagine there is a circle there, and around that you have a snake that is eating itself. Many snakes in this lecture. So. Well, also construction by Claire de Boer, you can make a blow up along a leaf. I will not enter into that, but it exists.
So,
yeah.
Functions work for your
smooth partition uniforms, yes. At least all those one. Blow up, I need to think, but yes. Okay. So, I still have to justify my definition by saying, how much time I have left? 8 minutes, perfect. By saying that leaves exist. I mean, that's things you hope. So from now on to the end, I'm going to say that leaf exists, theorem. I need to be slightly more precise after. Exists. So first I have to define what is a leaf. And just for a few minutes, just to make you more confused, I will define two different types of leaves. R leaves, reachable points, T leaves, the tangent leaves. Okay, so what's the problem? Well, if I have a point, I can consider all points I can reach from this point by following flows of vector fields in F. These are just called like 50 years ago as the reachable points. Okay. I can call that the leaf through M. I would call it the R leaf through M for a moment. The good point with the R leaf, it may be nasty, but at least it exists. And by construction, R leaves are a partition of M. So they exist on the partition M, good. But they are not manifolds, in fact they are, but they may not be sub-manifolds a priori. And second notion, T-leaf. That is a T-leaf through a point, so you have a point M, you want to have a sub-manifold, maybe immersed, that contains M, and you want that, I call it L, and you want that for any other point on that leaf, TL is TMF. So if the TLM is, I just take F, I evaluate at this point, all vectors in F, I get a subspace. And I want something more, I want them to be a maximum, because otherwise I just take an open subset in a leaf and it would be still a T leaf again. So I want sub-manifolds whose tangent space is what they ought to be, and which are a maximal among those. Okay, so now I have two notions of leaves, R leaves and T leaves. This one exists, a partition M, but there may be terrible things, at least this one, they are sub-manifolds by definition. Okay, so if I can prove R leaves and T leaves are the same, done. I call it leaf, and they are a smooth partition manifold of L. So all we have to prove is that R leaf and T leaf for a given point M is the same thing. Why is it not obvious? It's an example I out to Thomas Strobel, and where it comes from actually. The infinite comp. Of the infinite comp, it's all vector fields on R2, and here they can do whatever they want, but here they have to be horizontal. You see, if I take vector fields on R2, but on this half plane, they have to be horizontal. And here they can do horizontal, vertical, we don't care. That's a symmetry of R2 module. That's stable in the Lie bracket. But it's not finitely generated. And what are the R leaf for these points? Well, all points. We follow the flow like this, we go vertically, go back. There's only one R leaf, it's R2. But it's not a T leaf, but at this point, Well, the R leaf is everything. So in particular, V vector is tangent to the R leaf, and I don't want it to be tangent to the R leaf. It was a T leaf, because the only thing allowed is horizontal direction. So that's why you need directly generated. It's to invite issues like infinite comp. Okay. So 5 minutes left. How do you prove it? Well, you prove it. First, there is a proposition, which is really hard. So Alfonso actually published an elementary proof of that proposition, which says the following thing. And here we really use locally finitely generated. That if we have a vector field in F, its flow, assume it's well defined, maps F to F. You see? That if X is in F, then I take the flow at time t, assume it exists, and I push forward F, I need to get F. That's how. Okay, I have no time to prove it. I wanted to give an elementary proof. I think I have no time. So I have a better proof tomorrow that will use almost clear algebroid. I just give the better proof tomorrow. Better proof, I don't know. At least the proof people in Poisson structure should like, maybe. Anyway. Now, out of that, you can prove Weinstein splitting theorems type of a theorem. So you can prove that I'm going to restate it in local coordinates. We take MF, a singular foliation. We take M in M. So there exist coordinates. Oh, you assume dimension of TMF is, I don't know, A. And can show that there is, yeah, there is local coordinates where F, I could call it X and Y, where F is generated, about many X's and many Y's, is generated by, well, d over dx1, blah, d over dxi, and then some vector fields that only depend on the variable y. So not only it's purely d over dy here, but the functions in front depend only on y. Plus, all these functions vanish at 0. It's exactly a constant fitting theorem. Let's say that pi is sum of dpi dqi times something with transverse coordinates. Okay. So I'm saying that this proposition implies that. Why? Because the proof is like this. I just give easy proof. Well, it's by a recursion on A. I take my singular foliation, I take a point M. I assume this guy is not 0. Then I have a vector field that doesn't vanish. So by like straightening theorem, I can assume it's d over dx1. And then I have to use little bit tricks with the symmetries to say that all the other generators, first I can kill the d over dx1, and second I can kill the x1. Okay. And this implies that R leaves are T leaves. Because it's like this in these coordinates, at least if I take a reachable point, starting from M, if I am next to it, the only directions I can go are these the directions. So if I take the connected components of reachable points, it's a sub-manifold. And that's enough to say, exactly like in Poisson's symplectic structure, that's enough to say it's an immersed sub-manifolds. Okay, so the structure is flow of vector fields in F are symmetries on F. You can prove Weinstein-like splitting theorem. You deduce that T leaves are equal to R leaves, so you have a smooth partition manifold. I think I'm done, right? I just have 1 minute. Just to say that I just say again, all what I said for smooth partition manifold holds again. Traveling over leaves, it's annoying, it's always the same thing. Transversals have an induced singular foliations. Any two transversals are isomorphic. Locally, you have a direct product. And yeah, that's it. I want to say something about this theorem. It's really amazing how many times it has been reproven independently. So I spoke of the proof of Alfonso and Yuri Yudilevich. There's also Androidakis Kandalis. Before that, there's a proof by Dominique Serveau. Before that, by Dazor. Before that, by Nagoya. And before that, even Hermann in 1955. Thank you for your attention.
Well, thank you very much. So we have time for some questions. If people want to ask questions now. Or I don't know if there are also questions online. Nope.
So at what point in the proof does the counterexample where all the vectors are tangent to some lines on one side, but there's no constraint on the other side? At what point does it?
There.
How does it?
There. In fact, I already saw in a paper in the 70s the definition of the singular foliation. They replace the condition locally finitely generated. Well, they found it in Sylvain Lavau's paper. There's a flow of vector space in F is symmetry in F. That's enough to prove everything.
Other questions? Can I go against the consensus?
You sure?
Can we also turn things a little? I guess it's a matter of a discussion, but could we turn things a bit around and think that what you call a foliation is really a geometric structure on a foliation, which will be your first definition, a partition fold, a smooth partition fold?
Yes. Why not? You could say it's a smooth partition manifold, and you choose a subsymmetry of M module F, which which at least has to satisfy this. Why not? Yeah. But again, in examples, often the foliation is not given. Yeah. Just think of vector field scaling. I don't know. Just take any like a Whitney umbrella. Vector field scaling that a function.
But that's why I'm suggesting that it would be like a geometric, like a Poisson structure. It's a geometric structure. It has an underlying foliation.
Yeah.
These special type of models, they are like a geometric structure on a manifold. They have an underlying foliation too.
Yeah. So you are suggesting we could start with the underlying foliation. Yeah, probably. In fact, I don't know if there are smooth partition manifolds which don't come from this construction. That's a good
that was going
question.
to be my next question. But
I don't know. I think no. I think it's good question. I don't know.
all right, so we have a break now, correct? Oh, we have the official picture.
He's waiting for us to take a picture.
So let's just thank Camille once more.